Good afternoon. Today we will be discussing the work I have done for the Ag AID program in modeling cherry trees with color and depth data. My name is Marshall Saltz, and I am a junior at Oregon State University majoring in electrical and computer engineering. I have been working in this project as a part of Oregon State's participation in Ag AID, and my mentor is Dr. Cindy Grimm. Today we will cover the project introduction involving the background and motivation, tools used, process behind the project, and what work I have done, and then we will discuss what is next for the project and conclude the presentation. Tree pruning in the agricultural industry is a labor-intensive task that we have been working to automate. We have been focusing on sweet cherry and envy apple trees for these purposes. As you can see from the photos, these are two separate arrangement styles. Real-world testing has its limitations and logistical challenges. 3D modeling is a valuable tool for finding and making pruning decisions. We need to be able to locate prunable branches easily with a close-up view of the camera, as well as to estimate measurable traits of the tree, which in this case would be the branch radius. So, we need to create a virtual environment to model trees in that is as close to the real world as possible. To achieve this, I worked this summer to use camera color and depth, which is how far away it is, data to build 3D models of cherry trees. The materials I used were Python 3 with OpenCV for image processing, Matplotlib for plotting, NumPy for array processing, and scikit for data management. I used these libraries along with labeling software for image annotation and an Azure Connect camera to record. I ran all of this using the Linux distribution Ubuntu Jammy, on which I used FFmpeg to extract the individual images from videos taken of the trees. The workflow of this project begins with recording the trees with an Azure Connect camera to acquire the data. The individual images that comprise the data are extracted and then manually labeled using LabelMe, an open-source piece of software. The annotated images are given to one of the robotics students here and run using their model to output binary masks for the trees. I then take those binary masks and use an algorithm to turn them into three-dimensional structures for usage in robotic testing and training. First in the workflow is reading in raw data from the Azure Connect. This is an example of an image extracted from the camera's video feed. The camera reads in the depth, measuring how far away the objects in the image are in addition to recording video. To use this video data, I extracted the individual frames using FFmpeg on Ubuntu Jammy. Next in the workflow is image annotating. The images have to be labeled by hand, which takes 1 to 2 hours per image, with different labels and outlines around different parts of the trees in the video. We feed 50 or so of the annotated images to pass to Lee King's machine learning model so it can learn from those annotated images and process the rest automatically. Next, I use the processed and segmented images to produce a binary mask for each branch. This black and white image is what I use with the depth data to produce real-world measurements of the trees. I can use different masks for different branches, thus producing a curve with scikit and NumPy that imitates the curves of the branch. This shows how the binary mask produces a radius and a curve. The algorithm to determine the curve also acquires the distance away from the edges of the branch, thus giving us the radius of the trunk or branch at different points along the parts of the tree. A significant portion of this segment of the workflow relies on Alex Yu's follow the leader code. Using the radius and curve points, rectangular segments are taken from the branches and the average depth across those segments is outputted, helping reproduce the curve in 3D, which helps us determine to which trees and how the branches are connected, allowing us to better represent the trees in 3 dimensions. We determine connectivity again using Alex Yu's follow the leader algorithm. Determine connectivity between branches, or what branches are associated with which leader branches. We rely on the angles and depth of the endpoints of these branches. This part of the work is unfinished, but I designed a basic algorithm to determine connectivity which just needs to be implemented. All of those files and processes, acquiring the curve of the tree, its radius, and the connectivity between branches, will allow us to represent the structure of the tree three-dimensionally. Once I'm finished with the connectivity portion of the process, I'll move on to generating a 3D structure of the tree. Here is a review of the entire process. Start with raw data, end with a full 3D structure of the tree. All of the segments of the process highlighted in green are ones I either contributed significantly to or completed entirely. To complete this project, all that has to be done is to complete the ongoing 3D tree structure generation, finish annotating the 50 images, which take about 1 to 2 hours each, refine the 3D generation, and then the generated trees can be used to help make pruning decisions. Overall, this will improve the robotic testing process and enable the robot to better prune trees in the field. First, I would like to thank the AG-AID program, specifically Jordan and Paula, for this research experience. I would also like to thank Dr. Grimm for her support and mentorship, as well as Alex and Lee King for their work on this project, and Deanna, Nigel, and Luke for general support. Thank you for listening to my presentation, and here's my information if you have further comments or questions after the conclusion of this seminar.